Hello friends, I am Ashish Gambhir, and in this video we are going to learn about 2-bit comparator. 2-bit comparator. Okay, let us start with the definition of a 2-bit comparator. A 2-bit comparator is a combinational circuit which compares the two numbers, number A and number B. Both these numbers are 2-bit each. Okay, that means the number A is A1, A0, and the number B is B1, B0. So we have to compare these two numbers A1 and B1. Let us take an example. Say number A is 10, number B is 01. Mind you, these two numbers are binary numbers, not the decimal numbers. Okay, so when we compare the two numbers A and B, clearly we can see that A is greater than B, since it's 1 at the tens place and here it is 0 at the tens place. So the number A is greater than number B. The number A in decimal form is 2 and number B in decimal form is 1. Okay, so clearly number A is greater than number B. So we are going to make a digital circuit for a 2-bit comparator. Okay, so let us see that how we can do this. First of all, whenever we want to design a circuit, we have to make the truth table. Okay, so here also we are going to make a truth table. Let us see how we can do that. Let us make the truth table now. So we have two numbers, A1, A0, B1, B0. These two represent A, these two represent number B. And we have three outputs, A less than B, A equal to B, and A greater than B. Okay, so since we have two numbers A and B and each number is of 4 bits, each number is of 2 bits, so we can have a total of 4 inputs, A1, A0, B1, B0. So for these 4 inputs we are going to have 16 combinations. The 16 combinations are 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Similarly 1, 0, 0, 0, Similarly 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay, so here you can see that the 16 combinations are starting from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so as you can see here, when we see the first case 0, 0, 0, 0, so here the number A is 0, 0 and the number B is 0, 0. So number A is equal to number B. So we will put a 1 over here and 0 over here. Fine. Similarly, in the second case, the number A is 0, 0 and the number B is 0, 1. So clearly number A is less than number B. So we are going to put 1 here and 0 here. In the third case, the number A is 0, 0 the number B is 1 0. So clearly again number A is less than number B. So we are going to have 1 here, 0s here, and finally here also 1 here, 0 here. Fine. So in the same way we can complete the whole truth table. So here it will be 1 0 0. In this case you can see that A is 0 1 and B is also 0 1, so A is equal to B. So we'll put 0 here, 1 here, 0 here, then 0 0 1 0 0 1. Here it will be 1 0 0 1 0 0 1, sorry, here it will be 0 1 0 0 0 1, and finally in the last set of numbers it will be 1 0 0 1 0 0 1 0 0 and 0 1 0. Fine. So you can see here this is the complete truth table for our circuit, the design which we are going to make. You can say the 2-bit comparator. Now we can use this truth table to make our digital circuit. First of all, to find the expression for A less than B, A equal to B and A greater than B, we are going to use the K-map. Okay, so now we are going to use the K-map. Let's do it for A equal to B. Let's make the K-map. The lines are not coming straight. Okay, so here I am taking A1, A0. Here I am taking, sorry, here I am taking B1 and B0. So we know that it will be something like this. Here also 0 0 0 1 1 1 1 0. Okay, so to fill these entries we are going to use the truth table which we have made. So you can see that A equal to B. Fine. For A equal to B, we are going to locate the number of ones. This is the one here. This is the one. Here is the one, and here is the one. Fine. So for each of the case, we are going to see the minterm. This is the minterm. Then this is the minterm. This is the minterm, and this is the minterm. Okay, so let's fill it out. A will be equal to B when A1 A0 is 0 0 and B1 B0 is 0 0. Similarly here, here and here. Fine. So now we can write the expression. The expression will be A1 bar, A0 bar, B1 bar, B0 bar. Why we are making this expression? You can see here that we cannot do any kind of pairing. Okay. Plus A1 bar, A0, B1 bar, B0 plus A1, A0 bar, B1, B0 bar. This is for the third one, and for the fourth one plus A1, A0, B1, B0. So we can see here that we cannot minimize it further, but we can rearrange it so that we can represent this thing in some basic gates form. Okay, though you can directly make the circuit for this, but it is going to be very you can say bulky, and it is going to be having a lot of components. So instead of that, what we can do is we can take a1 a1 bar b1 bar common from the first term and the second term. Okay, so when we do that, it will be a1 bar b1 bar, and the leftover thing will be a0 bar b0 bar plus a0 b0. Similarly, here also we can take a1 b1 common, so a1 b1, the leftover will be a0 bar b0 bar plus a0 b0. This can be written as a1 bar b1 bar plus a1 b1 into a0 bar b0 bar plus a0 b0. And finally this can be written as a1 b1 XNOR. Okay, so this is nothing but XNOR of a1 and b1. Similarly, this can be a0 b0 XNOR. Understood? So here what we have done is we have made use of the truth table, and we have found the expression, the Boolean expression for a equal to b. Okay, so from the K map we were not able to make the pairs, we were not able to minimize the number of variables. So what we have done is we have written the expression for the a equal to b, and finally we have rearranged it. We have taken something common, we have applied the concept which we know, and we have found that the a equal to b, the circuit for that is going to be a1 XNOR b1 into a0 XNOR b0. Fine. In the same way, we can write the K map for the a less than b and a equal to b. Sorry, a equal to b we have already written. So a less than b and a greater than b. Fine. We can directly see the expressions for the two. So for a greater than b, the expression is a1 b1 bar plus a0 b1 bar b0 plus b0 bar a1 a0. And for a less than b, the expression will be a1 bar b1, not b1 bar, it will be a1 bar b1 plus a1 bar a0 bar b0 plus a0 bar b1 b0. Okay, so these are the three expressions, and using these three expressions you can make the circuit for the 2-bit comparator. Okay, so let me do it for you. a1 a0 b1 b0 I have made a line, I am taking the complement of it. Similarly for a0, I am taking the complement of it. For B1, I'm taking the complement of it, and finally B0. Okay, so we have seen that A equal to B is XNOR of two things. It is XNOR of A0 and B0. So here it is B0, here it is A0. Similarly, A1 and B1. Okay, and these two are ANDed together. So this is basically representing A equal to B. Fine. The figures are not that good, okay, but still it will work for you. Okay. Secondly, let's make the figure for the circuit for A less than B. For A less than B, the expression was A1 bar B. So let's make the AND gate. Here we require 3 AND gates since there are 3 terms, and these terms of course are added up. So I'm passing it through the OR gate. Okay, so the first AND gate is A1 bar B1. So here it is A1 bar B1. Then the second term is A1 bar A0 bar, A1 bar A0 bar into B0. Here it is B0. Then finally A0 bar A0 bar B1 and B0. Here it is B1 and here it is B0. So this output is basically representing A less than B. And finally for A greater than B, again I'm going to use the 3 AND gates. The space is less, so these 3 AND gates are sending their outputs to the OR gate. This output is going to represent the A greater than B, and the 3 outputs are 3 inputs to the AND gates are A1 B1 bar. Here is A1, here it is B1 bar. Okay, then the second term is A0. Let me make this, let me just extend it further. Okay, so the second term is A0 bar, not A0 bar, it's A0. Okay, B1 bar, and B0 bar. Fine. And the third term is B0 bar. So let me take this B0 bar from here only. A1 and A0. This is A1 and this is A0. Okay, so this will be able to give you the picture that how we are going to make the 2-bit comparator. Fine. The circuit is not looking that good, so we can practice this. Okay, thank you.